Okay, folks, let's look at how to properly solve test 2. So our first problem is turning an energy into a wavelength. So the equations we have are energy equals h nu and c equals lambda nu. Putting them together, you can say that energy equals hc over lambda. Well, rearranging these guys, you can say that lambda equals hc over energy. And this would give us an answer in meters. H, 6.6, let's say times 10 to the negative 34th. I'm just rounding. And times 3 times 10 to the 8th divided by my energy, which is 8.19 times 10 to the negative 14th. Make sure we check our units properly. 6 times 3, 9. Now, times if you just do the number portion, you should already have the answer. But using all the factorials, all the powers, I get something like this. I get 2.41 times 10 to the negative 12th. Well, that's because that's in meters. To turn this into nanometers, it's a 2.41 negative 12 meters. In 1 meter, there is 10 to the 9 nanometers. So you get B. It's still a really small number, but you get B. Full electron configuration of zirconium. Well, zirconium is the fourth element into the fifth row. So starting away, first row, 1s2. By 2s2, 2p6. 3s2, 3p6. 4s2, here's the hard part, 3d10, 4p6. And then since it's the second element, 5s2, 4d2. You had to have all this and this for full credit. Which of all atoms would be the largest? So the trend is left and down for largest. So the furthest left is cesium, furthest down is also cesium. So it could only be cesium. Now, next one is probably one of the trickier ones. Which column would the element with falling successive ionization energy belong to? So the first loss, about, we'll just say about 600. The second loss is about, we'll say it's 1100. But essentially 2 times the first one. This guy is about 5,000. So the difference here is about 600. The difference here is about 4,000. The difference here is about, let's say 6,500. Difference here is about 1,500. And that one, let's say 8,000. The difference here is about another 1,500. So where's the big jump? The big jump is between 2 and 3, meaning it has to be group 2A, not group 3A. You can easily lose 2, but not the third guy. Froggy FM, broadcast in Mercury at 103.7 FM. That's in megahertz. What energy is this? So E equals H nu. Nu can be in inverse seconds or hertz. So 103.7 means 103 megahertz, and in 1 megahertz, there are 10 to the 6th hertz. So that means we have 1.037 times 10 to the 8th hertz. You multiply that by your 6.6 times 10 to the negative 34th. And you should get something like D. D. Put these guys in isoelectronic order. The key here is increasing size. Most positive would be smallest. Most negative is largest. Isoelectronic means they have the same number of electrons. So we have aluminum 3 plus, followed by magnesium 2 plus, followed by sodium plus 1, followed by F1 minus, O2 minus, N3 minus, C4 minus. You may want to say F is the most electronegative, but they're all negatively charged. The more negative it is, the more repulsion, the bigger it is. So that's the way to do it. What is the condensed electron configuration of Mercury? So Mercury is on row 6. So starting from row 5, xenon. We always for condensed, we always use the noble gas. So row 6, 6s2. Here's where it's really hard. Goes to the F, 4f, 14. There's only 14 elements in there. Then it goes to 5d10. That's not 15. And that's not 9. There are 10 elements in that row. It's just the weirdness of the lanthanide and actinide series. Easy problem, easy problem. Say the molar absorptivity is this. And what is the concentration? So the Beer's law is A equals epsilon path length times concentration. So absorbance of 0.734 divided by 1.07 times 10 to the 4th times 1 equals C. We don't need the wavelength. The wavelength is where it's measured at, but it's not actually in the equation. So your answer is 6.86 A. How many valence electrons would be in chlorine? Chlorine, we consider just the S and the P. So correct answer is 7. Write the condensed electron configuration of germanium 2 plus ion. Key here, so germanium is in the 4th row. So germanium neutral would be argon 4s2 3d10 for p2. That would have got you half credit. So, but germanium 2 plus, so we remove from the P, then the S, and then the D. So you use up those 2 electrons to make it germanium 2 plus. Okay. Now, which compound would have the largest lattice energy? So first thing, it's look at the charge. 2 plus, 3 minus, 2 plus, 2 minus, 1 plus, 3 minus, 2 plus, 3 minus. So that these guys are, so are effectively 4, 6, 3, 6. First thing is you look at the charge. Second thing is you look at the size. So if you're comparing size, N is smaller than P. So lattice energy, N would be greater than P because it's Q plus times Q minus over the size. Small size means bigger lattice. So A, a lot of people miss this one. A lot of people miss this one. That's okay. On d orbital. D orbital looks like a clover leaf or a wheel and spoke. The flower is the F. The sphere is this. So there, the D is B. Predict the condensed electron configuration of copper. This one was a trick question meant to try to see who tried to, I can't prove you cheated if you got this one wrong, but it makes me kind of rethink you a bit. So this is, copper is one of the exceptions. I've told you, everyone, I won't test you on the exceptions because what is the predicted electron configuration of copper? Well, copper is the 9th element into the D series on row 4. So argon 4s2 3d9. This was the answer I was looking for. The actual, notice I wanted predicted, the actual B argon 4s1 3d10 because of a strange energy issue. However, I didn't ask anyone to memorize these strange occurrences. So the fact that you came up with the actual answer suggests you maybe got that answer from somewhere else and makes me consider how you maybe got that. I want you to be able to do this, not look things up. Last page. Highest electron affinity. This is actually kind of tricky. It's F. It's F. You would want to say, oh, helium should have the highest, but remember, helium has a 1s2. It's full. It's full. There doesn't need electrons. This one is going to be 2s2, 2p5, and it wants to go to 2p6. So it wants that electron. Well, this guy does not. Now, this one was not meant to be a trick question. It's supposed to be easy. How many ion pairs in a crystal structure? We're talking about like almost infinity. That there's going to be sodium and chloride, and then sodium and chloride, and sodium and chloride. I could understand if everyone put one pair, but the fact 25 pairs, 100 pairs, a salt crystal contains millions and billions and trillions of ions, little atoms stuck together to form a normal salt crystal. We simplify it down to one in the formula unit, but it's really billions and trillions. And finally, how many unpaired electrons would there be in cobalt? Well, cobalt is the 8th element into the D series. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the 7th element in. So 1, 2, 1, 2, 3, 4, 5, 6, 7. How many unpaired are there? 3. Name a scientist. Any scientist. Well, we had, everyone seemed to like Bohr for whatever reason. Bohr. We had Heisenberg. We had what, like Schrodinger. We had like Slater. We had Einstein. Surprised I didn't have more Einsteins. We had quite a few. There might be a couple I'm forgetting, but those are just a few that come to mind. That was the test.